Hello. In the previous chapters, we studied system of linear equations. When the coefficient matrix A is square, we have different methods to solve this. One of them is about how to use the inverse matrix to solve these systems, right? If A to negative 1 is x, right? Then x equal to A to negative 1b. We were talking about that, and we know how to check if a square matrix is invertible or not. And I think it goes a long way because we need to use row elementary operations, right? And I hope we remember that in order to find the inverse matrix if is x, so we need to write this form, and then from here we get the reduced row echelon form, right? Reduced row echelon form. And once you have reduced row echelon form and this part becomes identity, then this guy is the inverse of A. If this is not identity, so A does not have any inverse. Okay, and so the system does not have a unique solution. Okay, so of course that is a long way. We need to use another invariant. We need to find another invariant so that we can determine if A has an inverse or not. Because sometimes you don't need to find the inverse. Sometimes you only need to see if the system has a unique solution or not. Does that make sense? So if you just need to answer on that question, you don't have to find the inverse. You don't have to solve the whole system. It takes a lot of time. Okay? All right, that is the first motivation. The second motivation is this. When we study inverse of 2 by 2 matrices, we have A, B, C, D, right? We know that, if A, B, C, D has an inverse, then that inverse looks like 1 over AD minus BC. Here, D, A, negative B, and negative C. Okay? So look at this. Of course, this formula works even if AD minus BC is not 0. And we also talk about AD minus BC is not 0 means two rows are not proportional, right? Because otherwise, two rows are proportional. You use row elementary operations, and in the row echelon form, you have 0 rows, right? So this condition is pretty interesting, right? You have AD, the product on this, subtract the product on this diagonal. And this is called the determinant of 2 by 2 matrix. The value AD minus BC. AD minus BC is called the determinant of matrix ABCD. So this value helps you to understand if a 2 by 2 matrix is invertible or not. And of course, that helps you to determine if the corresponding system of linear equations has a unique solution or not. If the system has the form AX equal to B, right? Where A is 2 by 2 matrix. So, this example motivates us to determine the determinant of a matrix of the size more than 2 by 2, 3 by 3, or any n by n. Okay, so that is the main purpose of this video. Before that, let's talk about minors and cofactors. Suppose that you have some square matrix A. let's say Aij, or I can write this from A11, A12, and so on, A1n, A21, A22, and A2n, and then n, n1, an2, and so on, ann. You pick some Aij somewhere in here, Aij on the I row and the j column. Okay, so the minor Mij of the entry Aij is the determinant of the matrix obtained by selecting the ith row and the jth column of the original matrix. So what does it mean? Right now we don't know about determinant, right? But we know the determinant of 2 by 2. But we don't know the determinant of the general matrix n by n. Anyway, I have the following one. I say, yeah, if I have some entries Aij, I can determine the minor Mij of that entry. What is that? That is the determinant of the matrix obtained by deleting the ith row. So I just delete, right, this row and then this column. So if this is n by n, so the matrix obtained from the deleting the I and row and I row and j column would be of the sign n minus 1 times n minus 1, right? Is that correct? And then you determine the determinant of this. Okay? And if you have a minor Mij, you may define the cofactor Cij of that entry. So you have Cij cofactor of Aij is what? That is equal to -1 to I plus j, and here Mij. So basically, that is the difference between the minor and cofactor. So, it really depends on the I and j, right? Let's consider the following example for 3 by 3 matrix. Suppose that you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. You can find, let's pick A11. Okay. A11. So for A11, you have M11. What is that? That is the determinant of the matrix 5, 6, 8, 9. You see, because you already delete, right? You already deleted this row and this column. So the remaining part is 5, 6, 8, 9. And you calculate this determinant, you get 5 times 9 minus 6 times 8. 5 times 9 is 45, sorry. And then minus 48, which is -3. You see? So you have M11. Similarly, you can find, Mij for any Ij. So that means you have 9 values, right? 9 values. Mij. Because, I goes from 1 to 3 and j also from 1 to 3. Okay? So since you have 9 entries in the matrix A, you have 9 values Mij. I repeat again, right? But let's say in this case, yeah, you have M11, right? So from here you can find C11. What is C11? That is -1 to 1 plus 1 M11. That is -3, because -1 to to 2 means square is just 1. Okay, but if you calculate like A12, let's say this. So you have A12. What is A12? A12 is the determinant. I write that. Okay, determinant of the matrix A12. That is this guy. This guy, right? This guy. So I delete the first row and the second column. I have the following matrix: 4, 6, 7, and 9. And I find the determinant of this guy, right? So the determinant is equal to 4 times 9 minus 6 times 7. So you have 36 minus 42, and you get -6. That is the minor. And the cofactor of this entry C12 is equal to -1. 1 plus 2 times -6. And you see in this case you have -1 times -6, which is 6. You see? So cofactor and minor are not always equal, right? They are equal only at positions, at entries, when sum of I and j is even. Does that make sense? So you see, they are a little bit different, right? Now let's go back to 2 by 2 matrix. Okay, let's go back to 2 by 2 matrix. So let's say if you have matrix A, B, C, D. Let's find cofactors of all entries and minors of all entries. Okay, so if I have A right here, what is that? A, the M11, right? This is 11. So M11 is equal to D, because you already delete the first column and the first row, so you still have only D. Is that correct? And then the C11 is also D, because here the position is 1, 1. 1 plus 1 is 2. All 1 and 1 have the same, parity, right? So if I and j have the same parity, so, the cofactor should be equal to the minor. All right, let's move to B. So here is M12. M12 is C, but C12 is -C, because the position is 1, 2. 1 and 2 do not have the same parity, right? Okay, let's move to C. You delete this column and this row. You have only B, right? So I have M21 is B, and cofactor C21 is again -B. And how about D? You have M22 is equal to A, right? And then C22 is equal to A. All right, now look at this. If AD minus BC is not 0, means the determinant, right? Determinant is not 0. Then the inverse, A to -1, is 1 over determinant AD minus BC. And here you have DA, -B, -C. Look at this. And this. Can we see something interesting? The C11 is D. The C12 is C. Right here. Right? This is C11. This is C12. The C21 is -B. And the C22 is A. So, in general, maybe there is some connection between minors and cofactors. Is it correct? And what is the determinant of 2 by 2 matrix? AD minus BC, you see? AD minus BC. So if you look at this from point of view of cofactors, what can you see? You can see actually that is what? That is A times C11, right? Is that correct? D is C11 plus B times C12. You see? Because B, C12 is negative C. Or this is what? You might look at this like that is A times C11 plus C times C21. You see, the first formula says, yeah, you just take the sum of entries A and the cofactor C11, right, on the first row. So this is the first row I can write here, the first row. But this formula says that is the first column, right? You see that? Or at the same time, you might write, yeah, you can choose the second row. So what is AD, right? AD would be, so if I start from C, I can write that is C times the cofactor of the C would be times C21, right? Plus D times C22, you see? Or if you choose the second column, you have B times C21 plus D times C22. All these four expressions are the same, but from different point of view, right? It depends on how you look at this expression. AD minus BC. Okay, so we have some feeling, right, about the determinant and how we can use determinant to find the inverse of a matrix. You see this? If you look at this formula, yes, we might think about, the determinant of this form, along any entries or along any row or along any column, right? And if you look at this formula, you might think, yes, we can use determinant and you can use cofactor to find the inverse of a matrix. Agree? All right, let's move to the general definition of the determinant of a matrix, of a square matrix, of course. So based on that observation, if A is a square matrix of order n greater than or equal to 2, then the determinant of A is the sum of the entries in the first row. Here they write the first row, right, of A multiplied by their corresponding cofactors. That's what we discuss in here, you see, of the first row, right? In this case, they choose the first row. But that's okay, if you want, you can choose the first row. If you want, you can choose the second row or the first column or the second column. Okay? So that is what? Determinant of A. That is, determinant. This is also notation. The notion of determinant. So equal to sum of entries on the first row with, product, the product of entries on the first row and x cofactors, right? And then you take sum of those terms. You get the determinant. And again, you can show it. Actually, you can find the determinant using any row or any columns. Okay, so but in this case, in the definition, they use just the first row, but you can use any row or any columns. Don't forget that. Agree? Let's move to examples and see how we can use this formula. For 2 by 2, we already discussed about that. Let's talk about 3 by 3. A is 2, 0, 2, 1, and then 3, negative 1, and 2, 4, 0, and 1. Okay, let's find that A. Okay, that A. So, using this formula, you may need to choose rows or columns with more zeros. Because if you have some entries equal to 0, you don't have to calculate the cofactor of that entry. Is that correct? So I need to pick, row or entries or columns with more zeros. In this case, I see 0 in here, 0 in here, So you can pick like the first row or the first column or the second column or the third row. Okay, so let's use the first row. Okay, let's use the first row. I have that of A equal to I have 0. So I don't need to calculate C11, right? So I have 2 times C12 plus 1 times C13. Now let's find C11 and C13, okay? So what is C12? I can write negative right away because 1 and 2 in here are not of the same parity, so the sign is negative. I need to find determinant of the matrix 3, 2, 4, and 1, right? Because I need to delete the first row and the second column, right? So I have this is equal to negative 3 minus 2 times 4, which is 5, right? Here I have negative 5 with the negative equal to 5. Okay, perfect. And then C13 I can write negative because 1, 3 are not of the same parity. And then I delete the first row and the third column. I have 3, negative 1, 4, and 0 in here. So this is equal to negative 3 times 0 minus negative 1 times 4. So that is, again, I think here is 4, right? 4 with negative, so negative 4. And then you plug these two numbers into this formula. You get that of A is equal to 2 times 5 minus, no, plus 1 times negative 4. Interesting. Is it correct or not? So if I have negative right here, right? I have negative right here, 3 with 0, and then minus with the positive is positive 4 with the negative in here. It should be, oh no, I'm wrong. Here we don't have negative. We don't have negative in here because 1 and 3 are of the same parity. Oh my goodness. So I have 4 in here, right? I have plus 4. Sorry for that. So here I have plus 4. That's why you have, 10 plus 4 is 14. So that is the determinant of the matrix A. Okay? Please pay attention on this. Don't do a mistake like me. Now 1, 3 of the same parity. 1, 2 are not of the same parity. So if they are of the same parity, you have plus in here. You have plus in here and you have plus in here. Agree? Let's move to matrix of higher order. Let's pick 4 by 4. Let's find the determinant of the following matrix. 1, negative 2, 3, 0. Negative 1, 1, 0. And 2, 0, 2, 0, 3, 3, 4, 0, negative 2. So look at this. You have 4 by 4 matrix, right? And again, you need to find that of A. And again, we need to choose row or columns with more zeros. Which one? It is right here, right? You can see that on the matrix right away. So here you have 3 zeros, which is good because if those entries are 0, you don't have to find their cofactors. All right. So from the formula, the determinant of A is equal to 3 times C. Here should be C13. C13. Is it correct? So in order to find C13, I can write 3 and then determinant of the matrix obtained by deleting this column and this row and this column. So I have determinant of 1, 1 and 2, 0, 2 and 3, 3, 4 and negative 2. You see that? So it looks good to me, right? And again, I see I have 1 0 on the second row and the first column. You might choose the second row or you might choose the first column, whatever you want. But we already picked rows, right, in the previous example. Let's choose the expansion along the first column, okay, the first column. So this is equal to 3, that is coefficient. The first column I have negative 1 in here, times C11, right? Okay, this is already different C, right? This is already cofactor for this matrix, okay? And this is for the original one. So I have negative 1 times C11 plus 3 times C31, okay? Which is good, okay? We need to pay attention on the side. So let's say, what is C11? C11 is positive because 1 and 1, right? That is determinant of what? 2, 3, 4, negative 2. You delete the first row in the first column. So that is 2 times negative 2 minus 4 times 3, which is negative 4 minus 12 is negative 16. And then you can find C31 again with positive, right? Because 3 and 1 are of the same parity. So you delete the first column and the third row. You have determinant of 1, 2, 2, 3. That is 1 times 3 minus 2 times 2, which is negative 1. Okay? And then you plug these two numbers into this formula. You get determinant of A equal to 3, negative 1 times negative 16 plus 3 times negative 1. And then 3, 16 minus 3, which is, okay, around here, 3 times 13, that is 39. And that is the determinant of the matrix A. Okay, so based on this example, you might think about, if you have a matrix of n by n, right, and you need to find the determinant of this matrix. So you expand the determinant along some row or columns with more zeros, and you move to matrices of n minus 1 times n minus 1. And so on. You just decrease the order, right, of the matrix, n minus 2 times n minus 2 until you get 2 by 2 or 3 by 3, whatever you want, right? And that's how we can find determinant of a matrix of the order n by n. For 3 by 3 matrices, you have a very special formula for determinant. Okay, so let's talk about determinant of 3 by 3 matrix. Let's A equal to A11, A12, A13, A21, A22, and A23, A31, A32, A33. If you expand the determinant of A along any row or column using the definition, right, you will have the following. Determinant of A equal to A11, A22, A33 plus A12, A23, A31 plus A13, A21, A32 minus A13, A22, A31 minus A11, A23, A32 minus A33, A21, and A12. Look at this. Why can I write that very fast? Because I use diagonals in this case. So you can see the determinant of A has 6 terms, 3 terms with positive signs and 3 terms with the negative signs. Okay, so how can we determine that? Look at this. We have the main diagonal. This is the main diagonal, okay? So all terms with respect to the main diagonal will be positive sign. How? How to determine that? The first, the product of 3 entries on the main diagonal. Okay? And then, which is this guy is parallel to the main diagonal with this guy. You see? So you have A12, A23, and A31. The product of these entries with the positive side. Similarly, you have another entry another parallel line with the main diagonal. So you have A21, A32, and A13 with the positive sign. And then you move to the other diagonal. You consider almost the same thing with the other diagonal. Product of three entries on the other diagonal with the negative. And then the parallel one, you see, with this guy, with the positive. And the last one is this guy with this guy. You see? So, if you have 3 by 3, you can use that, idea to write 6 terms of the determinant of A. Okay? So let's do that. A is 0, 2, and 1, 3, negative 1, and 2, 4, negative 1, negative 4, and 1. Okay, let's find determinant of A. So I will use that formula, again, right? Sometimes you don't have to memorize this formula. You just need to memorize the idea, how to write all terms of these formulas. So I start from the main diagonal. 0, negative 1, 1, I got 0. Okay. Next, 2, 2 with the 4. So plus 2 times 2 times 4. And then 3, negative 4 with the 1. You see? Plus 3 times negative 4 times 1. So you have 3 terms with respect to the main diagonal. And now let's move to the other diagonal. I have 4, negative 1, and 1 with the negative. 4 times negative 1 times 1. And then negative 4, 2 with the 0. So that is just 0. I don't write, right? And then 3, 2 with the 1. You see? Minus 3 times 2 times 1. Is it? Let's find this. 2 with 4 is 16. And then minus 12. Here I will have plus 4 and then minus 6. Overall, I have 2. So that is the determinant of my matrix. Of course, you don't have to expand, right? Because this is 3 by 3. Okay? So in order to finish this video, I just want to remind about, one more formula, determinant of triangular matrices. Of triangular matrices. If you have such form, it's pretty easy to find, because you see you have triangular, let's say whatever you have, upper or lower, right? It's not important. So one of these two guys is 0. Let's say that, right? Because you have triangular matrix. Suppose that you have an upper. If you have an upper triangular, so all entries in here will be 0, right? And then when you expand the determinant along the first row, you have A11 in here, right? And then you delete that, you move to A22 and so on. Overall determinant of A in this case is equal to product of A11, A22, and so on, A and N. That works for the lower triangular matrix. So it's pretty easy. You see? It says that, yes, somehow we need to convert a square matrix into triangular form, right? Because in that case, you just need to take product of all entries on the main diagonal. Is that correct? But again, right, we will talk about that in the next video when we study properties of determinants. Okay? So I stop my video in here. If you have any questions, please feel free to let me know. Thank you.